Masud Karim, Chair, IEEE Just Student Branch. Uh, Welcome everyone to this session, Elementary Model Modeling, especially focusing on DC motors and AC induction motors. Today, our host will be Farhana Nasin Nabila. She will conduct the first part of this event and the question and answering session. And I will cover that. So, Farhana Nasin Nabila, carry on.
Assalamu alaikum and good evening, ladies and gentlemen. Can you hear me properly?
Yes.
Thank you.
Carry
I
on,
am
Farhana.
Farhana Nazneen Nabila, Joint Secretary of IEEE Joshua University of Science and Technology, and for the day. Thank you, sir. We extend warm welcome to everyone to this webinar organized by the IEEE Just Student Branch. Today's webinar is on elementary motor modeling, with a particular emphasis on DC motors and AC induction motors. We are excited to introduce our speaker, Mohammad Tariquzzaman, Assistant Professor at Joshua University of Science and Technology. Additionally, he is pursuing his doctoral studies at Oregon State University, USA. In a short while, we will dive into his research and learn about his. Now, let me introduce our speaker, Mohammad Amjad Hussain, engineer. Dr. Hussain has recently joined the Nuclear Radiation Laboratory at the University of Illinois at Urbana-Champaign, USA, as a postdoctoral research associate. Prior to this, he served as a senior scientist at the Institute of Theoretical Electrical Engineering, Ruhr University, Bochum, Germany. Welcome speech. Sir, please.
Hmm.
Amjad, sir.
Farhana, thank you. Thank you very much. So, thank you very much, IEEE Student Branch, Joshua University of Science and Technology. So, for organizing these events, organizing this seminar, and I would like to thanks Tariquzzaman, our assistant professor at Joshua University of Science and Technology, for this great initiatives. I really thanks him because he is inspiring our students. He is teaching our students how to do that, how to implement or how to modeling this one. So I think this is very good initiatives. One thing, Masood, if I want to break the one order, so Masood, can I ask you that the token of gift is prepared or something, and can we give it
Yes, sir,
before the presentations?
yes, sir, we can.
Anybody know Mehdi is there or not? He is not available.
So Mary sir is outside. He can't join now, but he will join later.
Okay, he
On
will join later, right?
yes, sir.
Okay. So okay, yeah, I will in the consent of Mehdi, or maybe I will take consent later from him. So can we give the token of presentation, token of gift to Tariquzzaman before starting his presentations?
No problem, sir. We can give it now.
So is it ready, right?
Yes, sir. It's ready.
Okay. So already Farhana, she already give the introduction about Tariquzzaman. So
Sir,
so
I'm
before
really
starting the
sorry for
presentation,
my net
please.
just messed up. My net connection was really bad. Let me continue it.
Okay, please continue.
Thank you, sir. Now it's time to extend our warmest welcome to Mohammad Tariquzzaman, sir. Mohammad Tariquzzaman, sir, he is currently pursuing his doctoral studies at Oregon State University, USA. His research revolves around hydrokinetic turbine energy conversion project and the enhancement of rural grid voltage stability through the implementation of grid forming inverters. These projects receive financial support from US Department of Energy's Advanced Research Project Agency, ARPAE, and funding provided by Portland General Electric, PGE. In terms of education, Mohammad Tariquzzaman holds both a bachelor and master's degree in electrical and electronic engineering from Khulna University of Engineering and Technology, Kuwait, Khulna, Bangladesh. He completed his undergraduate studies in 2016, followed by his master's degree in 2019. During his time as an undergraduate, he was the recipient of prestigious merit-based scholarship and received the esteemed Dean Awards on 3 separate occasions. That is quite an achievement. Mohammad Tariquzzaman sir is a researcher in fields of power, electronics, renewable energy, and machine derives. His, his contribution can be seen through his numerous publications in high-impact journals. His research interests span across various areas including power electronic, converter control, motor drives, and the integration of renewable energy system. We are delighted to share that this event has generated substantial interest within an impressive registration count. The registration count is over 80 participants, and here the number of IEEE members is only 30, but the number of non-IEEE members is 60 plus, and that is quite an achievement for us. It is gratifying to see such enthusiastic participation from a diverse range of universities, including both public and private universities from Bangladesh, as well as several universities from India. This diverse gathering sets the stage for a stimulating and dynamic learning atmosphere, ensuring fruitful interaction among attendees. We strongly encourage all participants to actively engage in the question and answer session after Mohammad Tariquzzaman's presentation, and it promises to be an excellent opportunity for lively discussion and insightful exchange of ideas. So, ladies and gentlemen, without any more delay, let us extend a warm welcome to Mohammad Tariquzzaman, and we can now focus on the presentation. And Mohammad Tariquzzaman sir, the floor is now yours. Please proceed with your enlightening presentation.
Hey all, thank you, and good evening. But I'm right now in morning in US, so kind of you can tell like you can see the past, and I can see the future in terms of like difference in time zone. But actually, I'm kidding. It's the same time frame right now. So today I'm gonna talk about a basic motor modeling. So it cannot be considered as a webinar because usually webinar presenter present their own research work, but here I basically go through the basic stuff. So I just wanted to violate the regular rules. So I wanted to ask the audience during the session, and also you can ask me any question during the session. So it's kind of like lecturing, not a webinar. So if it is okay for everyone, then we can follow that rules and then go ahead from here. So just need your concern.
So, okay. So I'm going to violate another order of the lecture or this webinar or seminar. Masood, can we hand over the token of gift to Tariquzzaman? Please
Yes, sir. We can.
carry on. And you start it, please.
Okay, sir. I'm just Just a minute.
Sir, is it okay if we carry it on at the end of the session?
I
Uh,
think
End of the
yeah,
session.
we can keep it later if you wanted to.
Sir,
I'm not.
uh,
Okay,
thank you.
thank you,
This,
thank
okay. So a big hand for Tariquzzaman. So
thanks.
everybody, please. So okay, Tariquzzaman, please start your and please Masood send the PDF file to Tariquzzaman later. Okay.
Thank
yes,
you.
sir.
Really
I will.
appreciate
Okay.
it.
Okay.
Thank you.
Okay, sir.
So I
Share your.
just turned off my camera and just wanted to sharing my screen. So I think everybody can see my screen right now.
Yes, sir. We can see your screen.
Mm-hmm. Okay. So without further ado, I wanted to go through the session plans today. I think some of the people already got the hands out for this presentation so that they can know beforehand what's going on and what sort of topic we might study today. So basically, our plan is like go through DC machine modeling, and underneath that DC machine modeling, we can go through like characteristic equations, then state space presentation, and then some sort of basic Simulink model. And then actually we run through all of these by hand today, so no worries, and we are not in a hurry, I guess. And then from there, we wanted to look through some basic control strategy, so you can focus on some advanced control later in your thesis or even in your higher study, like linear quadratic regulation or reinforcement learning, all sort of advanced control scheme. But it's a good way to start with how this control system works and how we can actually design a controller for like controlling speed of a motor or some other factors. So then from there we'll just go through some overview of induction motor modeling, and we might introduce like a space vector, which is widely used like mathematical tools, and then why we use that, and then if time permits we'll go through induction motor modeling as well. So there should be some question coming first, why we are arranging in this way, like why DC machine modeling first. Can anyone contribute with that? Like, do you have any thoughts on that, why we started with DC machine modeling other than starting from induction motor or whatever it is? From the participant, anyone can argue with that?
This machine is quite.
So I think
No,
the DC machine is more basic
no
thing
one
like
contribute. I can give you the answer. The reason is like DC machine is very simple in terms of operating principle and all that, and it's pretty easy to control. But these days, industry people use AC machine modeling and also AC motor. The reason because of that is like there is no brush for DC machine, and also sorry, there is no brush for AC machine, so the maintenance cost will be reduced, and modern control technologies evolved so fast, so we can control AC machine in terms of like equivalent to DC machine. So first I go through the machine characteristic equation. Don't be afraid about this mathematical jargon. It's quite easy to understand. So I don't know, I can write on that. Yeah. So here you can see like the back EMF is proportional to speed. So which I denote EA to be coherent with the figure here. And then this EA can be written in a form of like a constant times angular velocity. So this constant is basically known as like back EMF constant or even machine constant. And then there is another phenomena like torque, and torque is proportional to current. So you can encounter the same strategy we follow for back EMF. So that would be like electromagnetic torque equals to kT times IA. And then if you are wondering like how this KE and KT related, so I just put a question over here. So as I said, you can like communicate through this webinar, and you can ask or contribute with me to make this like webinar more like interactive, not one-way broadcasting. So I put a question like if KE is 6 volts second per radian, so what would be the value of KT? Does anyone have any guesses on that? Anyone from the audience or attendees? So I can wait another 10 seconds maybe, or I can throw the answer as well. So actually, those there you can see the form of unit is kind of looking different, but they're actually numerically the same. So this if this K is 6, then this KT should be also 6. So that's the machine constant we might need during the modeling. So I just wanted to introduce it earlier. So then if you able to kind of generate the equivalent circuit of the machine, then you can write the electrical characteristics equation like this way. So here you can see this VA is basically the input voltage. So that's the only thing we can regulate. So that's the key point. So that's VA can be like supplied through your outlet or through some other stuff like power processing unit or maybe power electronics converter or inverter, whatever it is. So this VA can be controllable. And then the equivalent, if we draw the equivalent circuit, then we have to consider like armature resistance, which is denoted here R sub A, and then inductance is L sub A. So we might later don't use this subscription notation and go through like RL and all that. And then since it's a electromechanical system, so we also have some mechanical parts. So which are include here, like electromagnetic torque and then angular speed and then load torque. So do we have any control on the load torque? We don't have basically. So this TL is considered as an uncontrolled input or disturbance sometimes. So if we split our idea into two separate domain of physics, then electrical characteristics equation will be like that, which is quite straightforward. You guys already know like what is KVL is, and then we just apply that KVL here. That's it, nothing fancy. And then for mechanical characteristics equation, we do the same things. Like it's basically a summation of torque is 0 across the operation, right? So that's that. This equation also known as a like swing equation sometimes, because it has a different version, like related the motion to power input and output. So that can be named as a swing equation, but the basic idea is the same. And then one parameter here is not presented, which is like T friction, which is very important because it's related to frictional loss of the machine. And we can summarize like whether the speed is higher, this loss can be higher, and there is a proportional constant for that, like B, which is known as a damping coefficient or even like frictional coefficient of the machine. So this B can be more challenging to design. There are some expert to do that, like modeling this B itself through bunch of empirical method or analysis, like freewheeling the motor and then come up with the value of B. So it's tricky, but we keep it straightforward and keep it as a constant for now while doing the modeling. And then here is basically just combine these two equation and made a block diagram representation over here. And here they introduce like J equivalent instead of J, but that's the same thing, like inertia of the motor. Any question up until now? If not, then I will move forward to the next slide.
Move forward, sir.
Okay. Another thing we need to deal with is like state space modeling, but we might wondering like why we deal with this state space modeling. What's the necessity of doing that?
Sir, for
So
complex system is
you can
necessary.
see the answer is right there, like on the first equation. So you can see I put this x bar derivative form, which is basically states, and states is the minimum number of variables that can detail the condition of the whole system. So then the variation of state is basically depending on some variable, like functional variable, input functional variable, or even with the state as well. So the change of state is dependent on the state itself and also other inputs. So that's why this equation is very powerful. But if it is not clear yet, actually we know the derivative is kind of deal with the future. Like if you write the derivative, I can share another screen here. I don't know whether you guys see my latest screen. So actually dx over dt, if we derivative these things, that means like x t plus 1 minus x of t divided by like the time step. So you can see through this derivative, you can know the future value of a certain variable or whatever. So we can, if we know the current value of the states, we can argue like we also know the future value, as long as we know the state space model for that uh, system. Sorry for switching back and forth. So now I just literally denoted all the variables here. Like this A is system matrix or state matrix. This B is basically control input matrix. VV is uncontrolled input matrix. And then this C is basically output matrix. This DU and DV is known as controlled and uncontrolled feed through matrix. And then this X is obviously states, and U is like controlled input, and V is the uncontrolled input. So just recall what we see in the previous slide, like the machine's electrical equation here, and then those mechanical characteristics equation here. Can anyone guess like how will it looks like if we transform this whole equation in terms of like state space modeling? Anyone have any guesses? Feel free to join with me. Otherwise, I feel like bored. Any cases from the audience? So I can help with that since we define states and that's have a derivative part. Do you see any derivative part here?
Yes, sir.
Yes, sir.
I can see like from the equation first, I can see this term is actually derivative portion, and from second equation, this portion is basically another derivative term. So we can just do some mathematical come up with the form that is close to this state space representation. So I just tweak this equation because this one is already in place. So just tweaking this equation and you will get this sort of form, which is uh, can be compared to the generic steady state modeling equation. And then, so the question will be, what will be the states for DC machine? Yes, the state will be omega m and then IA. These two will be states. So I'm thinking, is there any other states that we can think of? Anyone? So another state can be like the position of the rotor. And then with that, we can write the state space equation. So first one, you can see like I put IA, that is that, omega m and theta m, and it just writing these two equation in a matrix form. And as I said, there'll be another one, like the third one, which is known as theta m, or like position of the rotor. So that can be related to omega m, right? So which is basically, we know like omega m is a derivative of theta m. So I use that information to represent these three states of DC machine in terms of state space modeling framework. So you can see this one is basically the derivative of states, and that one is the like system or state matrix, and this one is states itself. And I split controlled and uncontrolled input into two parts. Sometimes they don't do that, so sometimes they just lump together these two parts into one. So here I prefer like splitting things, so I just divide it into like controlled and uncontrolled input. And if you wondering what will be the observability of this system, that quite straightforward. For our system, the like output will be the same as states. So the matrix of output matrix will be just identical matrix, and there is no impact on input and like both the input controlled and uncontrolled. So I wanted to head into control strategy or modeling approach, but control strategy later. But one key thing we need to remember is like this first equation. This is very important because this information can give you some sense like how you can do controlling and all that. So if you know the state space of a certain system, you can control the system from that moment. So designing a controller beforehand, you need a condition like you should have the state space modeling of that system. Otherwise, you won't be able to control that system. Yeah, you can control the system in other method like brute force method, but that might not be intuitive, or maybe ended up like getting some instability issue. So I can switch back to DC machine modeling. So I put some parameters. Does everyone see my screen right now?
Yes, sir. Can see your screen.
Yes, sir.
Am I audible?
Yes, sir, you are clearly audible and you are clearly visible also.
Yes, we can see your screen.
Okay. So I put some DC machine parameter here and go through each of those parameter, how we can infer if we don't know what's the value of that certain parameter. So I just wanted to walk around all this parameter list here. Uh, so I took a 200 watt 42 volt 1000 RPM motor and then assume like mechanical efficiency is 95%. So rest of the 5% gonna be like windage loss. So it's not considered core or like copper loss of the electrical motor. It's just mechanical efficiency. So based on that assumption, we can find out what will be like T friction, the friction loss. So before doing that, we just simply use that power equals to torque times omega, and from there we can know what will be the T rated. So in this case, we are considering like like the RPM and radian roughly like 10 times each other. So you can put like 100 radian per second instead of 1000 RPM because this is only valid when omega is in terms of like radian per second and while T is like Newton meter. So just simple calculation, it's like 2 Newton meter. And then since I already consider like mechanical efficiency is 95%, so we can like argue with that like the rated torque, out of rated torque 5% will be lost due to friction, and that's how I come with like T friction will be 0.1 Newton meter. And then the resistance, I this can be even you can find this in on the textbook, or you might have some sense like how the armature resistance is. So for this case it's like 0.2, which is quite high to me because it's a 200 watt motor. That's why this resistance is higher. And then the friction coefficient, as I said, that can be related to like T friction is related to B times omega. So make it simple. We consider like linear relationship. So this B is 0.1 divide by 0.1 is T friction divide by omega, and this omega is 100 radian per second. And then we can also find out like what would be the inertia of the motor if we know the mass of the motor and also the radius of it. So simply we consider the mass is like 2 kilogram and then the radius is like 2 centimeter. Based on that we calculate J and then L. As I said, this R is basically have like RS subscript notation, and this L has like LA subscript notation, but we just skip it. And then that's roughly based on the like experience. This sort of machine poses like 10 millihenry sort of. And then another thing we need to know, we already know this stuff, we need K now. And then as I said, this K is related to like the terminal voltage and also omega. So you can easily calculate if you just wondering, I can switch back. So I just shifting this equation. So this Ke will be Ea over omega. Sorry for my writing is very bad. And then based on this information, we can start with the state space modeling. So I just put A, which is system matrix, which is very important because it's relate the rate of change of states to states. So I just simply write it down what we seen in previous slides. So I can escape it, and then this controlled input matrix and uncontrolled input matrix is basically written in transpose form. So I think you already know, like put a prime on top is make it like transpose. So because these are like column vector, column vector or column matrix. So I write it down in a row way and just transpose it. And then this B, I think it's better called C on to align with that. This C is basically identical identity matrix for observation, and then those are fit through uh, matrices. Another thing I forgot to mention is like all the states should have some initial condition. So if you wondering like how you come up with states of a system, so there are several features of states. Number one is like it might be the all the cases is might be the derivative. There might be some difference, but I don't aware of that. So all the cases in equation, that might be a derivative term, and since it is derivative term, that should have some initial condition. So those two key important feature can help you design a system. And now with this information in place, we can just simply upload it on the workspace. So when we move forward from here, doing simulating already know or get those data from the workspace. I already built a, sample model, but I think I can go through every step by step so that all of us will be in the same page. So I just let me see version 1 maybe, or I'll- I like to keep these two side by side. Sorry for technical time consumption. So you can see you have those state space representation over here on the right side. So I can grab that. I don't know, it will detect it now. So I can write this equation over here. So you were wondering like what is Simulink is. It's nothing but representing some sort of equation, nothing else in block diagram. So you can see if even we know this equation over here, we can model the system. So you can see d omega dt 1 over j kt ia minus b omega minus tl is hot. It's the change of speed. So we can start with that and follow the step. Like let's say the best practice is like started from here and put the derivative, and then when you have the derivative term you can do integration so that this derivative become omega m, so that can be fit through to the equation. So that's kind of like general approach. Why we choose derivative portion first? The reason is like derivative itself is like step is not stable. If you do derivative operation, that's gonna be itself unstable. So rather prefer integration than derivative. So just put a constant block or the step block for TL. So that might be our TL. Step time will be 1 second, and then final value will be the TL value. Don't worry about it because we don't define TL before. And there is another input of the system. What is that? That's the control input, which we know as a VA. So best practice is like you name that block over here. You can do it quite easily. That's the input, and that's our disturbance or load torque. And underneath these two information, we can model all of this equation, right? Because these are two input. We need to have these two input. I'm sorry. I don't think it's an efficient way to do. So rather, I can pull up the modeling file itself. Here you go. So I did all this modeling beforehand. So I can just jump into the machine, DC machine model. So what I have done here is like choose two inputs, VA and TL, and then write the equation over here. And as I mentioned, it's a best practice if you represent derivative terms in terms of other variables and then make this derivative back to its original value by doing integration operation. Because derivative itself is not very handy. So best practice of doing modeling is like write the equation beforehand. So as it's dx is basically all the states. This x is actually the vector, state vector. So it's to system matrix, this BU and BV. So if we compare with this equation, it's the same thing, nothing fancy. It's the same thing. So you can see uh, all of this x is should be multiplied by AU. A is already defined in control space, so we don't have to worry about that. So you can see this A, which is defined in the MATLAB workspace, and these are all the states. So if we know the states, we can multiply it by A and then sum up with the input, like controlled input and uncontrolled input, just like this way. So if anyone has any confusion with that, can raise your voice, and I can also clarify once again, like this x is basically state, so it includes three parameters, that is IA, omega m, and theta m. Based on your control scheme, you might not need theta m, so you can skip that later, but for now I consider all of the three. And basically presenting the system in terms of this state space equation here. And these are like gain block. So if not change this gain block back to matrix form, it will do like element wise. So element wise multiplication is like not the same as this in block like matrix multiplication. So whatever the matrix is, this means whatever the matrix is, the input of the matrix will be multiplied uh, with that matrix as a like post from like not pre-multiplication, it's a post. And then you also have like choice of pre-multiplication, like this u first and then a. But for our case, it's like post. How about this one? This one also the same because if you looked at the equation once again, that's your v like bu. So that is beforehand like your input vector. So that's why it's also like post multiplication. And that's the same thing follows for uncontrolled. So with that, we can represent the all those summation into dx, and then this x. How can we know what is x? We can simply like integrate this dx and just feeding back to x. That's what we do here. Like integrate that 1 over by 1 over s, because it's a frequency domain representation, you know. Like 1 over s is denoted integration, and s itself is like a derivative operation. So that can fit through over here on the input side of this subsystem block, and that's end your like first portion of the this part. And then we have another one which is actually not required for control system, but it's required for like observation, how system like so the observable quantity here will be current, rotational speed, and rotation. And then if everyone know how I come up with this equation and how I can write that model in Simulink, you can also know how represent this observable output using these matrices, because it's shared the same thing, right? So underneath that you can see the same sort of form. So y is basically this should be cx in terms of like notation, but here we put b. I can change it to c. Then go back here, this one. That's our output matrix. So since we made any change here, you can see this workspace is not like updated. If you don't run this, it will not gonna be updated. So we have to run once again. That's what I do. And then going back to Simulink file. So that's all for basically DC machine modeling. It's quite simple, quite easy to understand. So now we wanted to look the output, what it looks like. So if you are wondering, I already preset the voltage input value will step up from 0 to 1. Sorry, 0 to 40. I think it should be 42 because we changed the terminal voltage back to 42. So I put that 0 to 42 will be happen and 1 second. And then if you are wondering, like sampling time is 0 means like continuous here. And then I keep it the disturbance from now is 0. And then run this model. Hopefully it works. And I think the newer model of MATLAB have this feature like login data over here without using the scope. So to visualize this, we need to click Data Inspector. Give it some time. Yep. And it's pop up. So the run can be you can see on that's a I would say like to if you make any tweaking throughout the modeling and how it reacts. So you can just simply compare with the last run data. So you can see like here are some that might be not in the same model. It's a different model. So you can even pull up that here. So for now, we need to see how it reacts. So any cases for VA? Actually, for VA, that's the controlled input. So we can whatever we want. But here VA, we set like a step response, and which is step from 0 to 1, like 0 to 42 at 1 second. Sorry about that. So what happened here? You can see, and then 0 for the whole time. So our input is fine. That's J. Now we can see like what will be the rotational speed of this machine. There is no control fed into it because it's just the step response, right? We control the voltage through a step. So we don't have a regulation or anything or even any feedback going on this like simple model. But later on, when we're dealing with the control strategy, we'll include that into our model and see if we able to regulate the speed according to our uh, like demand or whatever. So that's the voltage, like rotational speed. You can see it's itself stable because after that initial hookup, like all those noises, it can stabilize itself. But it's still that going back and forth in real life. If you wanted to do that, it will. It's kind of like cogging in the middle, like going back and forth and then stabilize. So which is nobody wants in the they should have some control scheme. And then if you are wondering how will be the current looks like, and then the current looks like this. So it's almost follow the same sort of noises that we have in the speed, but in a negative direction. And then from here, you can infer what will be the theta, because theta is basically summation of omega, right? So you can see it's a increasing fellow like this. So it's after that, when it is stable, that means the rate of change of theta will be constant. That's why it's like increasing or cruising higher value at a constant rate like that. And then we call this method as a state space. So you might wondering why we put space here. So the reason for that is like all the variables, like all the state variables can be represented in states. So how we can visualize that? We can simply change this time plot back into XY plot. So what this gonna do is like you can choose the variable on your own, because by default we can see this x-axis is basically representing the time axis, and then whatever you put on the y-axis will be that. So let me put on the x-axis is the current now, and then just click it on that side, and then y-axis will be your omega. If I hit that, you can see like they have a actually have a special relationship. So that's your state space, and those two axes is basically state variables. Usually people don't include theta for machine modeling, but we just did it. It's up to us. We are right now in a god mode, not in like dude mode. If you are in the dude mode, that means like you are using a default like block which Simulink can offer, but you don't have any right to tweaking internally. But they have like masking up top, so you can change the parameter yourself. But right now we can change whatever we want. So that's a good thing. If you customize your model for your research or anything, you can do it, right? You can change whatever you want, like which way you want it to see how it's performed. So that's basically the basic. And if I summarize what we learned so far, I think I put some summary in the next slide. First one to be provide system states, because it's key to modeling. As you can see, like heat states, and based on equation, we basically model these two basically equation we model this image, and that's totally right. Other than like when we assuming those parameters, there might be some ambiguity from the practical sense, but that's other than that, it's a valid model. There is no harm with that. And then uh, we should start with the derivation portion, like derivative portion, as I mentioned, and then integrate. So why we do that? Because derivative itself is like unstable, and integration is more also stable if you handle with like anti wind up or something. So avoid derivative. Once again, I make a caution note here, like avoid derivative, better use integral operation. And then state space is actually a geometrical space in which the variable on the axis are the state variables. So now I wanted to move to control strategy. So far, if anyone has any question or any like not know what's going on, can raise your voice right now. I think it's the best time to stop me and then ask your question. Can Masood conduct like question and answer session right now based on this portion of the say like
Yes, sir. If anyone
or
have any questions, you can just raise your hand or unmute yourself, and you can also put the question in the chat box.
oh damn, I literally mute my laptop. I couldn't hear you before. Sorry about that. Does anyone response before?
No, sir.
Okay, okay, okay. So then I move to the next section. It's a control strategy. So for controlling, we need to shape the analysis to frequency domain. So the first question will be why? Why we need to do that? The reason is like the response of a time domain system in closed loop can be inferred using open loop response in frequency domain. So if the open loop response in frequency domain is in a stable region, then should be in real life, the closed loop response should be in a stable region as well. So it's kind of easy to see in that way because it reduce the computational complexity and pretty easy to understand what's going on. And then we can, since it is like open loop response in frequency domain, we can utilize like Bode plot scheme. So if you put like PI controller, if you put PI controller in your system, why not PID? So that might be one question, but the reason is like, if you put the derivative once again, derivative itself is unstable, so you need to figure out a proper way to tuning the derivative. It's more caution situation. So even the reason for using derivative is like, other than dampen the transient response. But we can even achieve that overshoot reduction using like proper PI controller. So I put the controller transfer function as it's a straightforward like Kp plus Ki over S. You already know about this. And then open loop gain will be, uh, I'm referring to this right side block diagram. As you can see here is on the left is basically what we wanted to control. That's the reference value. And then we feedbacking the current states of X of S. So those are basically states. And then this GCS is like controller transfer function, and this GPS is like plant transfer function. So if you are wondering what is this GPS, that's basically our DC motor for now. And this GCS is like controller transfer function, so that should be PI for us. So if we with that, we can figure out what would be the closed loop transfer function. So closed loop transfer function basically the multiplication of these two, like open loop gain divide by 1 plus open loop gain. So for doing controller design, our main goal is like this reference should be equal to XS, right? This reference should be equal to XS. So how can we get that? Anyone has any guesses? How can we make sure like this reference value is equals to the feedback quantity? That can be achieved only when this GOL, that means open loop gain, is larger, right? Because if it is larger on top, then on the denominator you can see like this G omega L will be much greater than 1. That uh, like simplifies this equation is approximately equals to 1. So can we just boost G omega L, sorry GOL? Can we do that? We can do that by like changing the proportional and integral gain, because you can see this G omega L has two component. One is GCS, another one is like GPS. So GPS is, once again I repeat that thing, is like a DC motor model, that GPS, and this GCS is our controller. So we can't tweak DC motor model, but what we can do is like tuning this GCS. So right now you might have a question like, if we want like higher open loop gain, so we can just increase KPKI. That's it, right? We can increase KPKI whatever we want, and then this equation goes down to 1, like turns over equals to 1, and that fulfill our whole goal. But there is a catch on that. And what is the catch? Is like, you can see on that closed loop transfer function, we have a denominator which is 1 plus G omega Ls. So if this G omega Ls is equals to -1, what will happen? This whole system will gonna be like infinite, that means unstable, which we don't want it to have while we are designing the controlling parameter or everything, like tuning this KP and KI value. So how can we avoid that point? that point right there, like g omega ls is equals to -1, we should have to avoid that while designing controller. How can we do that? If you put that value, like if it, because these are all in complex, right? We know the main equation, all the representation here is like the complex number. So if we have lines, if we have one, like magnitude one, then the angle should be like -180 or +180. It doesn't matter because positive negative is the same thing. So usually in control system they took like -180. That's the degree we wanted to avoid. So if you put a Bode diagram here, then you can see there is a crossover frequency. What is crossover frequency? Crossover frequency is like where the gain of the Bode plot or gain of the system. Like what is the gain? Gain is here. The gain is like g omega l, open loop gain. As I mentioned before, in frequency domain we need to deal with this open loop gain, not the closed loop. So we can use this g omega l information and then see whether the system is stable or not. So here are some key like parameter or key, what I can say, like key significance or parameters, whatever you want. They these are like crossover frequency and gain margin and phase margin. These three. So what is crossover frequency? Crossover frequency is that frequency when the gain of the open loop gain is zero, basically 0 dB, and dB is like a decibel. It's a decibel, right? So if it is 1 bell, then decibel will be 10 bell. So in terms of decibel, and if you are wondering, this Bode diagram is basically log plot. So on the x-axis you can see 10 to the power 2, and then next one is 10 to the power cube. So it's like 100 radian per second. That one is like 1000 radian per second. So on this case, we intentionally choose like the phase margin is around like 60, and then gain margin will be infinite, whatever it is. So what is this phase margin? As I mentioned before, we wanted to avoid -180 degree. So if you see on the phase plot here, you can see during the crossover frequency, when the magnitude is 0, we can see still in terms of degree, it's like almost -120. So since it's almost close to 120, we can simply find out what would be the margin, because the margin is that dangerous point out there, like 120, 180, negative 120. That gives you like 60, around 60. Sorry. So if I just quickly shift over here, I might have another script. So there is a simple model of a AC machine, basically this one, but we can do the same use the same formula for DC machine as well. So you can see how I come up with that board plot that I show earlier is like all those parameter here, and then uh, you just need to find out what is the omega, like open loop gain. And then open loop gain is, that's the controller transfer function times the plant transfer function, right? And then that would be your margin. So we can do the same representation for our DC machine modeling. So before doing that, we need to shift our time domain representation to frequency domain. Because for controller design, you can see this GPS is basically in frequency domain. We can do that by doing some Laplace transformation, and then adding some like assumption. So what I assume here is like the disturbance TL is equals 0 and discard the mechanical portion from the electrical equation. That gives us this value. But if you are wondering, I can go through all the process from the beginning and then see if you have any follow-up question later. So I share another screen right now. So uh, before doing that, I just need to recall what our equation looks like in the time domain. So I just rewrite those equation here. D omega dt 1 over j ktia minus b omega m basically minus dl. And then dia dt equals to 1 over la va minus ke omega minus RAIA. That's the equation in time domain. Not a problem. We can switch back to Laplace transform. So if we do Laplace transform here, that's gonna be s over omega m s. And in Laplace, basically all the variables also denoted in capital form. So just ktia s minus b omega ms minus TL. We can write TL as a S as well, but I think that's okay. And then the second equation will be in the form of SIA S equals 1 over LA. This VA can be written as a K E omega, right? So we can use that word omega M S minus sorry. This is this not gonna work. This one is our input. Sorry for the confusion. And that's our back EMF part, which is already here. So the input can be, go back to capitalize, KE omega MS. I think capital omega is not looks like that. Actually, capital omega is looks like this. But okay, no matter. These are our two equations. And then, as I said, our controller variable is like VAS. And let's say we wanted to control the speed. So these are only controller input we have here, as I said. Remember, folks, like this is the only thing we can tweak and make this system stable or like controlling the whole system. So that's our only input here. That may not be the case for other system. There might be like several other inputs as well. But for our case, it's the only parameter, or it's the only variable, not parameter. It's the only variable that we can regulate. And then if we wanted to change the speed, for example, speed reference here, omega ms, that's we wanted to change. In that case, how can we like let the system know what would be the voltage based on the omega m value. So that can be done through like you know the transfer function. If you know what would gonna be your output and what is your input. So input always here is like VAS, and our goal is like controlling the speed. If you want to control a position for this motor, then simply that will convert it back to theta s ms over VAS. So these are two goals we need to achieve, like either speed control or rotational angle control. So how can we do that? Let's forget about position control for now, and widely used people using like speed control, unless there is precise mechanism like you need to rotate a robotic arm in a certain degree. In that case you might need like theta s over va, but in modern industry or anywhere you might work in later, they all will follow this like speed control mostly. So we can start with that. So omega ms over vas, if we know that transfer function equation, it would be easier to architect the controller. How? It's like if you know the feedback and if you know the reference speed, just comparing with the feedback value, and then there should be a controller. As I mentioned before, that should be your controller, just to align with that. And there should be your GPS. And GPS here is basically a transfer function of omega m and vs, nothing else. Because that's what we want, right? We input, like we want omega reference at a certain value, and then that should be your feedback. What is feedback? It's a omega, your current status of omega, and then compare here using a comparator, and then this this is here is basically the pi controller transfer function. And then this pi is making decision like based on the error signal it generated out through that comparator, and then this pi is basically give the sense what should be the next value for va to make this omega right. Because as I mentioned, this gps is nothing but that. Why not I remove this gps by omega ms over vas, and this is your vas. So like output will be your omega ms. I can even write this as omega reference s omega ms. So for example, we want 10 radian per second, and currently we have 6 radian per second. So that will feed back here. Here will be 6 radian per second. That would be 4 radian per second. And then this controller want more omega m. So it what it will do, it will send a message like decrease VA, so that omega m will increase, or even increase VA. In that way, you can increase IA, and that IA will increase the torque, and it's accelerated and going back to 10 radian per second. So as long as this controller working perfectly within a second or within within a some sort of response time, there should be a stable reason, like that's your case, like reference omega reference, and it's gonna going up and settle down at that value. And if you tweak once again, then it's going up and settle down. So that's the whole scenario. So main key takeaway here is like we need to find out what is the transfer function. So
So,
now I just, yeah, yeah, sure.
so sir, we are using basically PI controller that it reduces the rise time.
Uh, yes. So if unless we use like PI controller, what will happen if you set like 10 radian per second? For example, this one is missing. Then what would happen? It will not gonna change this VA because VA is not changeable at that point. So it might be settled down at some other point like that. Is that answer your question? And then
Yes.
another thing is like if you only use proportional gain, then what will happen? Proportional gain is basically amplify your error, and you will not achieve this zero steady state error uh, other than like integral gain, because integral gain is all time. What is the issue with integration is like summing up summing up the error, right?
Yes, sir.
Every time what's the magnitude of errors, so that's summing up. So in that case you can reduce that steady state error down to zero. Response time, phase margin, and transient response time. So you have to come up with idea like there should be some trade-off. And well-known well-known or well-established assumption is like making this phase margin around 180 degree, sorry, phase margin around 60 degree. Because if you have like more phase margin, like if you can even do like phase margin around like 120 degree. But the problem with that will be, since phase margin is 120 degree, uh, the transient response time will be reduced. So if there is certain change, then to catch up with that reference, you might need to wait too long time. But that makes your system more stable because there is less overshoot and less tendency to instability. But arguing and trade-offing between these two factor, most people come up with like 60 phase margin is better. Now I wanted to switch back to our say, sorry for shuffling shifting every time. I don't have any choice. Oh, I forgot to mention another thing. So as you said, like we're um, that should be in capital. This I over V, these both are in capital because it's estimate, but it's not an issue for us. So you can see like this I over Vs. So as you said, like as you said, how we control omega over V, like that's the transfer function. So how we control omega, we can control omega based on regulating this V, right? But dealing with V times omega will be much more complicated because you can see there will be more like some square terms, because this s over l plus r, 1 over s over l plus r, and 1 over s j plus b, these are the multiplication at that time, right? Omega over v, that's the multiplication is in of these two term. Like let me pull up this term here and that term here. You should need to multiply these two, so that gives you like omega, that will cancel out I, over here and this I, and you will get like omega s over vs, and that would be our like 1 over j sj plus b times 1 over sl plus r, right? So you can already see like it's ended up some s square value. Those are maybe complicated to deal with, but we can split it down. That's the best feature of this controller. Like you can adopt like cascaded pi controller. How is that gonna work? Is like split this transfer function. Like the objectives of this controller is like controlling the speed. So we can split this transfer function into two parts. One is like omega over I, and this is your current loop, and then this current can be represented in terms of like current over voltage transfer function later. So the reason of doing this is like it's simpler than maybe if you wanted to use omega over vs will be complicated. So we can use another inner loop. This is known as a like inner current loop. This one is known as an inner current loop, and that one outside. So it's known as a in like outside speed loop. So there are some other things you need to consider here, like what would be the speed of inner current loop. Generally speaking, this inner current loop has like higher response time, like sorry, less response time and like higher crossover frequency. And then this outer speed loop has like less crossover frequency and response time. So what I mean by that is like, let's say this require like 10 radian per second. Once again, follow that same example, and right now it's 6 radian per second. So it tell the current loop like right now 10, it said 6, so it's come here, and then it says to current loop like increase the current, because it's there is a still positive error, so increase the current. This current loop generally acting first, so faster than this loop. So if it said increase the current, and it's instantaneously increase the current, so it will not see how this inner loop is function, because it's so fast. So based on this error signal, if it wanted to say like say increase 2 amps current, then okay, you got it. And then later there will be increase 6 from 8, for example, and then there will be error like 2, and then it said increase the current 1 amps, and then increase the current instantaneously. So like this speed loop, as I said, it's kind of slow response, and this inner loop is faster response. So how can we choose like faster inner loop and like slower output outer loop? That depends on your crossover frequency, right here, right there. So general assumption or like thumb rules is like if the inner current loop is like 100 hertz, for example, then outer loop will be like 10 hertz. So it's like 1 over 10th relation between inner and outer. Any question on that? So ideally, if this you can see there is another like closed loop system on top, which I marked here. So if this perform well, then you can say like the gain would be of this subsystem will be just 1, right? Because that's our key takeaway the from the previous closed loop transfer function. So the transfer function of this closed loop will be 1. if you see from the perspective of a speed controller here, because it's acted like 10 times faster than what you give command in your output loop. But why some people not use cascaded PI controller? Because there might be, if there are like several subsystem, like several loop out there, then maybe, say for example, if I wanted to use like position control over here, then we just need to add another comparator and then another controller, and that will gives you like omega reference. And this is say for example C, that's the omega s, so this one is C theta s. Sorry, I can't use my pen here. So, and then that should be your theta reference, and then current value of theta, you need to come up with another transfer function between omega and theta. So that would be theta over omega. And we already know what is theta over omega. Can anyone contribute with that? It's already written here. It's just 1 over s. So then we can find what will be the theta, like the position, and just feed back here. And that's the way you can control even the position of a robotic arm or whatever. If you are gonna add up, like, definitely you're gonna add up some motor, right? Whether it is DC motor or AC motor, all actually share the same thing. It's just the equation down there that might be different. Okay, but all share the same theme. And then, as I said, what would be the response time of this loop in that case, like this position? We said it's 1/10, right? So inner loop uh, working at a frequency 100 hertz, outer loop working at a frequency 1/10 of that inner loop, that means 10 hertz, and then outer loop would be 1/10 of that, that means it's 1 hertz. For example, that's the assumption. So we might increase the inner loop around like 2 kilohertz or something. Then the outer speed loop will be 200, and then position loop will be like 20 in that case. Any question up until now? If not, I can pull up the MATLAB. So let's do controller design. What we need those transfer function, right? So these are the current controller, that's your speed controller, and that's your position controller. We can skip position controller for now and just deal with current and speed controller. So first we need to tune the current controller parameter like CIS, and then we will go through like speed controller parameter. So just current transfer function will be we need to define S as a transfer function like this way. Then current loop, so I can, it's omega I, is omega I as a current transfer function, and that is related to 1 over what is the SL, S times L plus R, right? And then you need to know what would be your CI is. So that's gonna be KP I plus KP I divided by S. That's your current control loop. control transfer function. And then open loop will be, open loop gain for this is like G open loop I would be gonna be equals to hi times C sub I. That's your open loop transfer function, right? And then we need to see the Bode plot. So Bode plot is simply uh, Bode this, or I better choose merging because it will gives you the face merging and gain merging at the same time. So that's that. We already know what is L and R, but we don't know what is KPI and KII. So these we need to know, or even we can tweak this value like KPI. We can assume this value, for example, like 1, for example, and then KII as a 0.1 to start with. That surely gives us some margin plot, right? Let's see. Yep. So you can see we don't have any control on that crossover frequency and also phase margin up until now. But after introducing this CI like controller block, you can actually tweaking this change KP value, for example, as a 2. So you already know, like if I increase ki, then the phase margin will increase. Is that the case? Yep. So previously it's 100%, whatever it is. So we can tweak the gain margin and also tuning this KPKI. Or there is a simple tools called like PI gain tuner, PID tuner. You can use that as well. So how can we do that? So there is a special tools like just in case. So you can see all the information. That's the best way to search about any function. It's like help and then whatever function you wanted to look at. So for our case, it's like PI tune. So you can see bunch of different way we can represent a system. So for example, here, if you wanted to know what would be the value at the output, that could be like C, and these are like structured. These are arrays, all the variables in structured form. So you might need like C dot KP, C dot KI, something like that. And then in terms of tuning information, you need to do like first, this G is basically plan. Sorry. this this one is like your type. So which type of PI controller you're gonna use, whether it is PI or PID. Omega C, that means omega C is basically crossover frequency, and you might also have like considering phase margin. But by default, I'd say they're gonna use like around 60 phase margin. So let's do that. Let's consider uh, for example, since it's controller, that's your choice. You can choose it. And then our plant is like h of I, right? I put that here. And then we wanted to deal with what sort of controller? PI for this case. So just put PI here. And another thing we need to do is frequency. So since we are doing kind of for 200 hertz. So like 200 hertz, since it's a cross frequency, we need to multiply 2 times pi. And then we don't need that right now. Let's run this. And here we find what would be the value of kp, and we set that specific or and then we want pi value, and pi value we can use like 60. Instead of 200. So kp would be equal to e from the top over like be, and then this ki will be like this. That's your open loop gain, and we need to observe is that performs well or not. So let's hit once again, and you can see that's basically our rate in terms of radians per second. We have 200 pi over it's 0.256. That over here you can see, and by default it choose like phase margin as 60 degree. So there are a bunch of different way to tuning your controller, like CISO tool is another part your plant like H of I. Then there will be pop-up designer work, and then even here you can also tweaking the crop frequency and phase margin by doing that, or even focus. And best thing is that you can also see the step response out of this, like how the step response is changing based on that, and then come up with what would be the value of pi and uh, like gain coefficient values. So that's the other way to tune the pi controller. So uh, I can even go with like the next session, like frequency speed control. So for speed control, you also do the same procedure, but instead of hi, like this transfer function, you need to use that transfer function, this one. And in the Simulink, you need to architect your model in this way. I think I'm out of my time. I'm sorry about that. I might do another session in that case, like go through rest of the portion of the topic. And so far, if you have any question, I have a few slides left here.
Sir, how much time would it?
I think it would be take more time because okay, let us try in that case because it's already 9:47, like 10:40 in Bangladesh. I don't know. Should I go for it? Like tweaking the simulation block once again and let you know how it's work. So like instead of using this step response, I can discard that and then use those add block real quick. I want bound shape and then that would be your comparator, and you need another gain block like pi block, pi controller block. So either you're gonna use this pi controller block or you can custom it by yourself. So the architecture will be not difficult because we already have this planned model right over here. That's the planned model. We just need to add the controller block across it. So here gonna be your current measured input, and here will be your current reference, and there should be another block which basically I don't want to do rush on this, so I might better use another slot if you have time, because this
Yes, sir,
gonna
we
be
can arrange another meeting.
yeah. And as you see, like this is not like a webinar thing, so we might do over like Zoom or something else. Yeah, because it's more like a class or tutorial, not webinar. Because generally in webinar they show all the outputs without like going through or walking across the process. But I want here to like go through across the all steps, and then you can learn from that other than throw you some figure or plots. So as I said, we can do the same method for the speed control. Let me do that first. So that's your current controller, and then here is your speed. So let's say hi omega, and then these are related to sj b. And then since we are using like 1/10 method, so like crossover frequency will be 20 hertz, not 200 hertz. That's very important to deal with like cascaded pi. You should reduce the outer loop and like keep the inner loop faster condition, and then change this c omega maybe. That gives your kp. This is our speed loop now, so change that. That would be, yep, that's your open loop gain. So you might see, okay. Oh, sorry. I changed that one. So that's your first figure, and I think this one is not anymore. hi. Sorry. Line 47. Oh, sorry about that. Okay. So now you can see like last time the current controller has like 1265 radian per second or something. And for this case is like speed loop. So we wanted to reduce the speed or the response time by 1/10, like elongate the response time 1/10. So that's why the crossover frequency is reduced like 126 radian per second. And phase margin, as I said, like by default it's 60. So that's the way you can also tweaking like speed controller loop. And the same thing you can also do for uh, like if you wanted to do position controller, then you also come up with that. Like for position, we already know theta would be 1 over s, right? Theta is 1 over s times. That's all you need. Like response time from omega to theta is 1 over s over here. And then you can argue with that like the controller PITOT will be simply 1 over s, that's the planned model. And then you can find out kp and ki value for position controller as well, and then use the margin plot, and you can look through that. It's actually maintain those sequence as long as you select this crossover frequency correctly. So I might actually show you some already pre-built motor block. So this is for induction motor, so which I don't even touch today. So you can see, I just want to show you how it's worked. So this one is your speed loop on the left, and then this the job of the speed control loop is generating the current reference, right? So that's happen here, and this job of this controller is like generate the control signal. And as I said, the control signal is only the voltage, and then so you can see the output is like the voltage. And for AC motor, there are two components like DAU. So you can see like two separate block. But don't worry about that. It's the same architecture, nothing else. And then the practical motor is basically having like three phase, not the two phase. So it's go down to transformation like DQ to ABC, and then underneath that is your like induction motor model. It's almost the same what we are looking here, like this decimation model. If time permits, we can show you those. So those are the same thing, like uh, machine model, and up top on the top model we have those controller. So another key thing here missing is like how we regulate this voltage. We are always mentioning like this voltage can be changed. Sorry, this voltage can be changed. So how can we change this voltage? It's actually job for power electronics, which is missing in this model, because we keep it like system level modeling, not like switching level modeling. So there are two different modeling scheme. One is like average model, another is like switch model. So this can do your job quite easily, but if you wanted to do like high fidelity modeling, then you need to jump up and consider those switching, like power electronics inverter circuitry arrangement. I think with that, I need to finish this session. Like require for control display tuning the PI coefficient, crossover frequency, and phase margin. Phase margin keep at 60 degree. At that point, it's perform better, like in terms of transient response and also stability consideration. That's a kind of like middle point. And I couldn't able to go through induction model and all that and all the rest of the slides. So thank you everyone. If you have question, you can ask.
Okay,
Yeah, go ahead. Karim, go ahead.
so maybe there's nothing
Mhm. Okay.
So, so now I would like to thanks everyone who have participated and have joined this session, registered for this session, and have participated in the Q&A session. Thank you everyone, and for session like this, if you want to arrange us, maybe for Yasmin, Tony, if you have any question.
Sorry, I was not trying to raise my hand. It was a mistake. Sorry.
Okay. So, and for more information and to join even like this, follow our Facebook page or LinkedIn page, join our public group, and you can also subscribe to our WordPress email service. We have email services, and thank you everyone for joining this session. With the hope to see you again. I'm ending this session. If there's nothing to talk about anything,
Okay. Thank you, everyone. See you soon.
thank you, sir, for
Thank
your
you, sir.
time. Okay.